Welcome everyone to this latest edition of the FHE.org meetup. For those of you that were at the FHE.org conference, good to see you again, and glad to see that there is so many interests in FHE in general, as always. So today we are going to be talking about large integer arithmetics with homomorphic encryption using the Concrete library. And we'll also take this occasion to introduce some of the latest features we've launched today in the library, namely a much more developer-friendly API for people who actually do not know cryptography. So I think in the case of the people in the meetup, you're probably going to find the API very boring for what you want to do. But for every other developer on the planet, which is everybody minus 1,000 people pretty much, it's going to be hopefully a lot easier to use homomorphic encryption. So Jean-Baptiste is going to be presenting today. So he's working at Zama, and he's the one who's leading the efforts on the large integers, and I would say more generally, everything that sits on top of the core library at Zama. JB, the floor is yours.
Thank you for the introduction. I'm going to share my screen. Can you see the screen? Yep. Yeah. All right. So yeah, let's talk about the homomorphic large precision integer using Concrete. So first, a little reminder about what is fully-homomorphic encryption. So let's start with an encryption of a message X. So we will represent the ciphertext with the blue line and the little lock on it. This means this is an encrypted data. So in this case, this is the encryption of the message X. So in fully-homomorphic encryption, the idea is to have several data that are encrypted, and we want to compute several operations. So first of all, we are able to compute the addition. So for instance, we have a ciphertext of X, a ciphertext of Y, and we want to compute the addition between the two of them. And in the end, by using a specific operation, we are able to obtain the addition of the two messages in an encrypted way. So that when we will decrypt the resulting ciphertext, we will obtain the sum of the two messages. In the case of fully-homomorphic encryption, we are able to do addition, but also we are able to do multiplication, which is based on the same principle of having computation over ciphertext, and which gives us the result over a ciphertext. So this is really useful in the case where a client wants to protect his data from outsourced server, and he wants to do the computation. So in this case, the server will do all the computation and then send back the data to the client, and only the data will be revealed to the client when he will use his private key to decipher the ciphertext. So this is the general principle of fully-homomorphic encryption. So in our case, we are particularly interested into the TFHE scheme. So the TFHE scheme is a fully-homomorphic encryption scheme. And so the idea will be to take small messages. So in this case, messages over p bits. And this will be our open message. So the first step will be to encode these messages into a machine word size. So meaning that here we represent a Q, which is equal to 2 to the power of 32. This means that we are computing over 32-bit integers. And this is quite convenient to work with our current laptops, for instance, or the current global processors. We are working over 32 or 64 bits. So the first idea would be to take this message and to put it into the most significant bits. So this is shifted by delta, basically. And then we also add some error. So the error is required for security reasons. And then this gives us the encoding of the input messages. The second step is about the encryption of the messages. So in this case, we are going to use a private key S plus some random values A, and we are going to compute the scalar product between these two vectors. This gives us a scalar, and this scalar is added to the encoding we previously computed. And in this case, all the information is basically hidden from an external person who does not have access to the secret key. So in what follows, we are going to use a lot the plaintext representation. So keep in mind what we are always working with encrypted data, but if we want to see a little bit what is going on inside the ciphertext, we use this representation because this is way more convenient. So in this case, we have an encryption of a message M1. So once again, this is the plaintext representation, but this represents generally an encrypted data. And we want to compute an homomorphic addition using the TFHE scheme. So we have two of the messages that are encrypted. We are computing the additions, and then there are two phenomena that are appearing. First one is that the noise is growing, meaning that the red part, so the red part on the left, on the right side of the ciphertext is growing. Plus, we can also see that when we are doing a computation of an addition, this also grows the size of the global message we have. So this might be problematic, in particular when the noise grows too much, because it might also overstep over the message spaces. And in this case, basically, we are overwritten the information containing the messages. This means that the decryption will be incorrect in the end. Hopefully, there is a magical operation with TFHE, and this operation is called the bootstrapping. So the bootstrapping takes as input a ciphertext. So we assume that the ciphertext has a lot of noise, but in the case where the message is not yet overwritten, otherwise, for sure, it's already a lost thing. So in our case, there are a lot of noise, but this does not touch the message. And in this case, so we will compute what we call bootstrap. So the bootstrap takes another parameter, which is the bootstrapping key. This is kind of particular key, just saying that this is a public key. So this might be given to the untrusted server so that it can do the computation of the bootstrapping by himself. And then using the bootstrapping as a black box, this gives us the same messages, but with a reduced noise. So in practice, this is really useful because we can do a lot of computation. And when the noise grows too much, we compute a simple bootstrapping, and then the noise is reduced, and we are able to compute as many operations as we want. The particularity of the TFHE scheme is to provide an operation which is programmable, meaning that further computing the bootstrapping, we give just a function as input in bootstrapping. So at the moment, we're just saying this is a function, like in a very generic way. We'll see more in details later. And then we give this function, and at the same time that the bootstrapping is computed, this also computes a function, meaning that at the end, we recover the function applied on the message. So this is like really convenient because it's very, very general. We can compute any univariate functions. So this is really a good thing. And the good thing is that this is for the same cost as just computing bootstrapping. So at the same time, we're able to reduce the noise and to compute a function. However, even if this operation is like really, really powerful, this comes with some constraints. So in particular, this requires to have 1 bit of padding. This means that the most significant bit should be known on the whole time during the computation if we want to ensure the correctness of the bootstrapping. So this is quite a problem because this means that we have to, all along the computation, to know how much our message is growing so that we are sure that the message is not going over this padding bit. And then for sure, we will lose the value of this padding bit, and this is a problem for the correctness. So we need to be sure that all the computation stops before this most significant bit. In order to have a measure of this kind of thing, we'll define 2 parameters. So first, the message modulus, which is kind of the message input size. Plus, we'll define a carry modulus, which is the definition of how many level operation we are able to do. So using this, we are able to measure how many operations we can do without overwriting over the padding bit. The second constraint of the PBS is that on the way it's constructed, so we are getting into the details now, but the way it's constructed, we are only able to compute over small messages. So this is a big constraint because in practice, the messages are like restrained to the size of 8 bits, 8 bits, at most. So we are only allowed to compute with small input size. And this is quite problematic because in practice, we want to have a large size to have as many applications as we want, computing over the fully-homomorphic encryption paradigm. So the question we want to try to answer here is how can we efficiently compute over homomorphic large integers? So by large integers, we mean larger than 8 bits. So to answer this question, we will have 3 different parts. The first one will be about concrete. The second one will be about the inner mechanisms that are used in concrete to compute over large integers. And then we will have a focus on the function evaluation over large integers. So maybe let's start with a simple demonstration. So in this case, we are simulating like a server and client thing. So in the left, you have the server, and on the right, this is the client. So here, the client wants to outsource its computation and to send it to server. The server will compute all the operation required by the client in a homomorphic way, meaning that it will not learn anything from the input of the client, and then send back the result in an encrypted way, and the client will decipher it in order to recover the result of the computation task. So here we have a simple thing, like we want to compute over FHEU in 3, which are basically the same type as the unsigned integer over 3 bits. So this is the homomorphic equivalent. So let's say we start with a simple computation of that. So let's say we want to compute, I don't know, like a multiplication followed by an addition. And so we are working with integers that are small because since we are over 3 bits, we only have like, we're only working modulus 8. So let's take like small values, 3, 5, 7, and do the computation. So the circuit is sent to the server so that it knows what it needs to compute, and all the values are encrypted. So in this case, the server computes homomorphically all the operation and sends back the result. And when we decrypt the result, we see that we have the same result as expected. So for sure, the client is computing over the clear text to see that the computation are correct. We can also do like a little bit more complex operation. If we stay with small integer at the moment, let's say we want to compute some bitwise operation and comparison. And let's take simple values. And this is doing the same thing, basically. So we can see that we can do classical operation like the arithmetic ones, plus some more complex operation dedicated to bitwise string and comparison over. So keep in mind that everything is done over encrypted values and everything is done in an homomorphic way. And so the other novelty is about the size of the input that we can choose. So in this case, we can have a formula over 16-bit integers. So I don't know, let's take a more complex computation. So in this case, for sure, we're working with large integers, and this comes at a cost. So for sure, the computation will be a little bit longer. So we will see how it works more in detail in the following slides. So yeah, keep in mind that the timing are here very, very low. I think the Zoom thing is not helping us in this computation. If we try like maybe a more simpler computation, still over large integers, let's say, I don't know, A and B, something which we know the results before encryption, and you see that in this case this is much more faster because the operations are much simpler. So this shows that now using the concrete we are able to make computations over 16-bit integers, which was before impossible. So let's go back to slides. And let's have a little look about the new release of concrete. So concretes come with, this is kind of a framework when it comes with a lot of libraries. So at the moment, we have the concrete Boolean, which was already released a long time ago, which allows the user to simply compute over Boolean's values. Now we also released a new library, which is called concrete-shortint, and which allows the user to basically compute any operation he wants over small integers. That was why the name is called shortint. So this means that integer less than 8 bits. Build upon this library, we are building the concrete integers which allows the user to compute over unlimited size of integers. So for sure, in practice, if you want to have computation quite efficient, we are limited, but in theory, we have no limitation on the precision we want to use over the integers. And build upon all these crates, we are proposing a new API, which is now just the name of concrete. And this API allows anyone to compute over homomorphic data, meaning that you don't need to have any cryptographic background if you want to use concrete. You just need to know how to code in Rust. So let's have a little look on more in details about the libraries. So the first one is the concrete-shortint, and in concrete-shortint, we are going to see this as the user view. So the user, when he wants to use concrete-shortint, has to fulfill some information. So he has to fulfill the size of the message he wants to compute on. He has to fulfill the number of level operation he wants to work. Plus, he can say if you want to work or not without a padding bit. So for now, it's a little bit blurry because we saw before that we needed a padding bit to compute all the operations correctly, but we'll see later that it might be released as as a constraint. Then it has the choice between a lot of operations. So each homomorphic operations comes with 3 flavors, which means the unchecked, checked, and smart ones. So the unchecked versions do the operation no matter what, meaning that we are not guaranteeing that the operation will be correct after the decryption. But this is the faster way to compute the thing. So if a user is like has a lot of background in cryptography and knows what he's doing, this is the way to go. The second one is more to try something. Maybe it means that it might have some error in the computation, and if you might have some error, this will return an error saying, okay, I don't want to compute this thing because it might return an error and I'm not guaranteeing that the result is correct. Then the last one takes everything in end, meaning that the computation will be done for sure, plus we are sure that the computation will be done in the correct way and the user has nothing to do. So in particular, as we have seen before, we want to be sure that the padding bit is not overwritten. And in this case, the smart operation will take care of clearing the carries for the user. This also means that to compute the same operation, let's say an addition, for instance, the time is not constant between the operation because from time to time, the smarts will take care of computing a PBS in order to remove the carries. And in terms of available operations, we have all the classical arithmetic operation, meaning the addition, subtraction, all this kind of thing. Plus, we have also the bitwise operation, the comparison, the PBS, and something which is more new and fancy in some way is the bivariate PBS. So the bivariate PBS allows you to compute bivariate functions. So it means that instead of having, like we've seen before, a PBS computed only over one value, in this case, you have 2 ciphertext, you want to compute a complex function over it, you can simply use the bivariate PBS to do so. Sorry, just a little thing about it. So because at the moment, we put under the carpet something which is quite complex, which is about the cryptographic parameters. So in order to simplify the life of the user, we propose like many parameter sets, and the choice of the user will be only about the input sizes. This means that if the users choose, I don't know, for instance, I want to compute over messages that are encrypted over 3 bits, and I want to compute like some leveled operation, and I want to have my carry buffer, which is also of size 3. You will just choose a set of parameter entitled param_message, this kind of thing. So this is quite an informational name. It will just choose these parameters, and it will be sure that the computation is correct. This means that all the noise problems are abstracted. So for the end user, it's like very useful because no one needs to worry about this thing, and the computation will be sure to be correct. So for sure, everything is about probability error. In this case, you will have the correctness with probability of 1 minus 2 over 2 to the power of 13. So it's like a pretty cool error probability. So build upon the concrete-shortint traits, there is the concrete integers. And so in this case, since it is using the shortint as a building block, for sure, the end user has to fulfill the same operations, meaning it has to fulfill the input precision, the number of the operation, and if he wants to use or not the padding bit. Plus, you have to choose between 2 decomposition strategies, meaning the Radix and the CRT one, and if you want to use single key or multi-keys. So at the moment, it might be a little bit complicated, but we'll go into further details on all this kind of decomposition. Exactly as in the case of the shortint, we have many flavors of the operations, and we have also a lot of available operations. So at the moment, for sure, there are less operation, but we are trying to complete it from time to time and adding all the things that the user might need to compute over the integers. For sure, if you want to compute a PBS, there are also a little bit of complexity, which has the choice between 3 different variants of a PBS. And so this is the same thing we are going to further details later. But what we see is that even with simple to use API, in the end, a lot of operation and a lot of choices has to be made by the user. And so in order to simplify all these things, we are fulfilling a new API, which is only the new name of concrete. And in this case, the only thing that the user has to give is the input size. And then he can do the computation. So with the input size, in fact, he will choose between default types that are proposed with the library, or he can define also its own types if you want to work with like particular spaces. Otherwise, the types we are providing, for instance, are the booleans, like the unsigned integer over 4 bits or unsigned integer over 16 bits. So there are many more of them. And this is just a choice. So once the user knows the precision of the message you want to work on, this is just a declaration of a type of a new variable with a particular type, exactly as you will do with the Rust classical thing. So without taking care of the homomorphic part. And then if you want to do an operation, you simply use the symbols that are the classical ones, meaning just a plus, so to do an addition of this kind of thing. For sure, as we have seen before, since the operations are not the same between the shortint and the integers, all the operation might not be available for the integers, so the list of operation depends on the type you are using. But in the end, this simplifies a lot the life of the user. He can do all the computation in a homomorphic way without getting any knowledge about homomorphic encryption or more generally about cryptography. So if we have a little bit of look on the new API, this always starts, we're still in cryptography, so this always starts with the generation of the key. So first, the user has to choose the size on the message you want to work on. So this is simply done with this thing. Say, okay, I want to enable to work with 8-bit integers. Then it generates the key with a simple command generates key. And then since we want to work with outsourced computation, we want to set the context for the server. And this is simply done with this command. So this is all about the initialization of the library. Once he has done that, he can start to work on. So let's say that in this case, he has 2 clear computations, so 2 messages he wants to compute. So first thing, he will start by encrypting. And so he said before that he wanted to work over 8-bit integers. So this is the type of the thing, FHEU int 8. And then he just wants to encrypt the message. So he called the function encryption over the message. And since this is like a private computation, he uses his private key. This is the client in general. Then doing the computation, so we can say, just for saying the thing that in this case, the computation will be done on the server side. On the side of the server, simply compute like an addition. And this is all like just A plus B. So everything is hidden for the user. Like we don't know that we are working with homomorphic computation and complex things. Everything is like as simple as if we worked with clear inputs. And lastly, you will use this private key to decipher the results and obtain the result of the computation you wanted. So to make a little bit of the comparison between the the last concrete version, which was the 0.1 and the new one. So this is the same code for doing the same thing. But in the case of the first concrete version, a lot of details are given to the user. So he has to know about cryptography because he has to set the parameters. There are a lot of complex parameters like the BS key level, all these kind of things. So if you're not a cryptographer, guys, you don't know about all these things. Here, everything is hidden, plus the type of the ciphertext is also hidden. So you don't know about LWE, RLWE, all these kind of things. This is just hidden to the user. The encryption, when using the previous version of Concrete, relies on encoder, and all these things is also simplified in the case of the new version of Concrete. And then we want to compute an addition. So if we want to compute over 3 bits, we want to do modular operation, basically. So if we want to add the modular operation and be sure that operations are going to be correct all along, then we need to do a bootstrap of everything. And all of this is also hidden to user because all the operations that are wrapped into the Concrete library are based on the smart operation of the underlying crates. So if we take like more complex example, we want to compute multiplication. So multiplication is based on using Bootstrap. So you have to know that to call the correct function in the previous version of Concrete. Plus, as previously, you need to compute also a Bootstrap to be sure that you are computing over the correct modulus. In the case of the new version of Concrete, you just use the multiplication symbol between 2 ciphertext and you're done. And if you want to compute like a more complex function, you also need it before to know how to deal with this kind of thing. Meaning that having a bootstrap over 2 inputs, so I said if I want to compute a max function, this is a bivariate function because I'm going to take 2 ciphertext as input. And so in this case, if you want to do this kind of thing, it's kind of complex because you have to know a little bit of cryptography and what to do in order to have the correct results. And this thing is also wrapped into the concrete to say, okay, I want to compute a bivariate function. So I'm just calling the bivariate PBS function, and I'm precising which function I want to compute. And this is all done. And you are sure that the result will be correct. Okay, so now we have seen a little bit of magical things. Let's now dive into a little bit more details. So this will be more about cryptographic stuff. So how to implement the large integers using TFHE. So the first idea is to use the Radix decomposition. So Radix decomposition, let's start with a message, let's say, which is over 16 bits. And the idea will be to split the message in many parts. So in the case of the Radix decomposition, we are choosing a basis to do the decomposition. So Radix decomposition is very common. We are used to work with a basis which is equal to 10 in real life. Our computers are used to work with a basis which is equal to 2, for instance. So this is like a very common way to decompose the thing. So in our case, we'll take the large messages, split it into small parts of the message, depending on the basis we are using. So in this case, we are going to have 4 blocks of 4 bits each. And then each of these messages is small enough to be encrypted using the TFHE scheme. So then we encrypt all the blocks and abandon them. And finally, the complete ciphertext is given by the collection of the underlying ciphertext. So let's now say I want to compute an addition over this Radix decomposition thing. So we have 2 messages, M and M prime, and we want to compute the addition. So if we have a look on the composition of each of the ciphertexts, so in this case, we are taking a simple example to have less block and to see better what is happening. So in this case, we say we have 2 blocks for each of the ciphertexts. So this means that we are going to compute an homomorphic addition between each of the ciphertexts. And if you want to have an inner look into each of the ciphertexts, this means that we have 2 messages that are here, each split into 2 ciphertexts. So we have each part into a ciphertext. Then we are doing the addition on each part. This means that we are going to have a noise which is growing, and we are also using one of the bits of the carry buffer. The good news is that we can see that even if we are doing homomorphic work, in the end, this is compliant with the classical Radix arithmetic we are used to. So if we want to compute multiplication, it's a little bit the same thing. So now we have a look, and it maybe reminds you something about your old school, I would say. So how to compute the multiplication using a schoolbook algorithm. So in this case, we have to compute the multiplication between each blocks. So meaning that we are literally using the school multiplication thing. The cool thing about that is we don't need to compute all the blocks, because in fact, we are working modulo B square in this case, since we have a message which is split in between 2 parts. So we are computing modulo B square. So one of the blocks does not need to be computed. And so in the end, we get the multiplication of both our large integers modulus B square. For sure, it exists more efficient algorithm than the schoolbook one. And so, for instance, we can cite the caret super one. But the principle is the same. One thing about the Radix decomposition is about the carry propagation, because once we have done some operation, the carry buffer getting full all along the computation. But we cannot get rid of the carries like that, otherwise the computation will not be correct. This means that we need to send the carry of the least significant bits to the most significant bits. So let's start and say, okay, I want to have the carry. So we will use a PBS to make a carry extract. And we will get a ciphertext which contains only the carry. Then the carry, we need to add it to the next ciphertext. So we will get another ciphertext, which is the sum between the message, the M1 message, which is the most significant bit in our case, plus the carry. Then in this case, since this is the most significant bit, the carry might be get rid of as easily as just throwing it away, because we know that we are working on the square. So this does not have any impact on the correctness of the computation. So we get rid of the carry simply, and then we do the same thing with the least significant block. And in the end, we get messages with the carry buffer that are clear. And we still have the correctness. So if we do a little bit a recap on the Radix thing, this is quite practical because it allows to represent large integers like the uint 12 or uint 16. You can do all the modular arithmetic operations on it, but it has a big constraint. This is this carry propagation, because in practice, this is like using a lot of PBSs. So this is sequential way to do, because if we increase the number of blocks, we need to do the carry propagation between all these blocks. So this is a sequential operation, and it's computationally costly because it requires to use a lot of PBS. So we try to change the decomposition, and now we'll use a CRT decomposition. So let's start with large messages. But in this case, we are going to use the Chinese reminder theorem, that was the CRT bins. And so in this case, to do CRT, we need to choose a basis, which is a little bit different from the Radix one. So in this case, we are going to use prime numbers, prime pairwise numbers. And in this case, we are able to compute modulus a big Q, and the Q is defined as the product of all these primes. So in this case, we choose a basis, which is almost of the size of 16 bits to have comparison with the previous Radix decomposition. So in this case, you are going to use 5 primes, and this leads to 5 blocks. And the blocks are different size. For instance, the N0 block is only over 3 bits, whereas the N1 is over 4 bits. But this is the same thing as in the Radix decomposition, meaning that we have small enough messages to be encrypted into different LWE ciphertext. And so the collection of all these ciphertext give us the CRT decomposition of the large messages. So this represents a large integer. So if we want to compute addition, this is basically the same thing as in the case of the Radix. So we'll compute the addition over each blocks. The cool part is that we can parallelize everything since each block are independent. This is due to the homomorphism given by the CRT theorem. So in the case of the addition, if we just forget for a moment about the carry, this also be done over the Radix decomposition, as all operations are done in their own blocks in some way. But in the case of the multiplication, this is the same thing, and this cannot be done using the Radix decomposition. This means that in the CRT decomposition, we are able to do the addition and all the arithmetic operation in a parallel way. And this is like very, very much more efficient than in the case of the Radix decomposition. The thing is now, we don't need to have a carry propagation between the blocks since each blocks are independent. So we still need to have a carry cleaning because the carry buffer is still growing all along the computations. So in this case, it's also the same thing. We will do like a carry cleaning, and this can be done using a PBS. So we just extract the message using a PBS, and then the carry cleaning is done. And this is the same thing that using everything in parallel is possible because blocks are independent. So everything in the CRT is done in parallel, and this is like a really cool thing. Okay, let's now focus on a more complex subject, which is the function evaluation over large integers. So let's start a little bit about more precision about the TFHE scheme. So in TFHE, there are many ciphertext types that are the LWE, that are the ones we are working on since the beginning of the presentation. There are the polynomial variant that are using, that is called the GLWE thing. And so this is the same thing, but we are working with polynomials. And there are also another types, which are the GSW, and basically there are a collection of GLWE. So we don't need to have a lot of details about it. The only thing is that we are going to use it in the next slides. So just remind that in green, this is the GLWE, so polynomials, and in the yellow thing, this is like GGSWE, so a collection of the previous one. If we have an overview of the PBS, so this slide will be a little bit more technical, but we will not dive into all the details. But this is here for more information purpose. So the PBS of TFHE is composed of 4 major steps. So the first one is like modulus switching, where we are just changing the ciphertext modulus. So yeah, and then we have the blind rotation. So this is like the important operation in our cases. So this gives a little bit more of details about the way to represent function into the PBS. So instead of giving a real function as input, we are giving a lookup table of the function, which is abbreviated here as LUT. And so a LUT is simply all the values of the function for some inputs precision, meaning that if I'm working over 2 bits, I will have 4 outputs possible for my function. And so the LUT will represent all the 4 outputs of the function. In the blind notation, we are using the PBS, the bootstrapping key. And this gives us another result, which is LWE, but we don't care about that. We are able to get back to an LWE and all these things. So just for the sake of precision, we know that we have to do a little bit more things in order to have the evaluation function over the message using the same key, but we don't care about the data for now. So one thing to remember is the blind notation, and the blind notation allows us to make a rotation over a lookup table. And this allows us to evaluate correctly the function using a message that has been encrypted. And this is done doing a rotation. So if we want to compute this kind of PBS over large integers, as we said before, this is not possible using this, this process. So the state of the art gives us a possibility, which is called 3PBS. However, in practice, the 3PBS is not very efficient because it does not scale very well with the number of blocks. In practice, if you want to go further 4 blocks, for instance, so when I mean 4 blocks is always to say I have a large message, I have a decomposition, which gives me 4 ciphertext to represent 1 large messages. And if I try to apply a 3PBS on it, it's going to take a long time. So we are kind of stuck with the precision we can use with the 3PBS. So here we are going to see 2 alternative ways to compute PBS. The first one is the PBS for CRT, but it comes with some restriction on the function class you can compute. And then we will see a new PBS, which is also called WU PBS. The WU is for the without padding bit. And so the advantage of this PBS is that it scales very well with the number of blocks. It doesn't need any padding bit. And this is compatible with any representation we want to use, meaning the Radix or the CRT one. So the CRT PBS is really simple. As previously, the idea is just to compute PBS on each of the blocks in an independent way. However, even if it is really efficient, because basically having the cost of a PBS is the same of having just the cost of a PBS over 1 block, because we can do everything in parallel. It has a major restriction, which is about the class of function you can compute about it, because the function has to be compliant with the homomorphism that the CRT proposes. And so if you want to compute like a little bit weird function or not arithmetic function, you might have problem. For instance, if you want to have the value of the last bit of the messages, since the CRT decomposition doesn't fill the same repartition of the bit, you cannot compute this kind of thing. So this is very efficient, but this has some constraints. So a more general way is about using the WU-PBS, but the WU-PBS uses a lot of small bricks. So let's start to have a look into the details of each part of the WU-PBS we're going to use. So the first thing is an operation which was defined into the TFHE paper, and it's called the circuit bootstrap. So let's say as input, we have a message which is encrypted, and the message is only 2 bits, so B1 and B0. The idea of the circuit bootstrap will be to transform this ciphertext into two ciphertexts that are encrypted in a GGS way. So let's go a little bit more in details. So we start with an extraction of the bit, and we start by giving the B0 bit. Then we need to do the same thing over the B1 bit. So in the end, we are getting 2 ciphertexts which only encrypts 1 bit. This thing cannot be done in parallel because of the way the bit extraction is implemented. So we need to have a loop over it, and so we cannot do this thing in parallel. Once we have our 2 bits encrypted, then we want to transform them into a GGSW, and this is done by the circuit bootstrapping, which is abbreviated here as CBS. So we are starting from a message encrypting many bits, and in the end, we are given many ciphertext only encrypting 1 bit, plus we have changed the type of ciphertext. More details, the CBS, for the ones who want to have a little more detail about it, are composed with the PBS and the functional key switch. So now we need to have a look about the LUT representation of the function. So in practice, the LUT will be represented as the last column of the thing, which is the out column. And this contains all the possible values of the function. So in this case, we have 4 bits as input. So we have 16 outputs for the function, for each possible values that each bit can take. So we need to work a little bit on this representation, and the idea will be to start by packing the LUT and splitting it into many LUTs. So what does it mean? We are going to take the first bits, so the most significant bits, and pack the thing. So the first 4 values, we are going to pack them into another LUT, which are only dependent on the B3 and B2 values. And we are going the same for all the possible outputs we have. So in the end, instead of having 1 LUT, we are splitting it into 4 LUTs. And then we are going to use 2 strategies to evaluate correctly the LUTs over it, which are called the CMX tree and the blind rotate. So first, we are going to have a CMX tree. So using our decomposition previously, now we only have input bit vector over 2 bits, and then we have only 4 lookup tables. So the idea here will be now to choose the correct lookup table depending on the value of the bits. So remind you that all the bits are here encrypted. This is on our input messages, and we want to compute a function over these encrypted messages. So the choice of the LUT has to be done in an encrypted way. So the CMX tree, as the name says, is based on the CMX. So a CMX is a simple operation which takes 2 inputs and which takes also a selector, which is here a GSW, so an encrypted bit. And using these encrypted bits, we are able to choose the correct value, and in the end, we obtain an encryption of the function evaluated on this bit. So this allows us to choose the correct thing. So by using a tree of the CMX thing, we are able to choose the correct bit. So if we are going back to our previous example, for example, with the 2 bits, let's say, for instance, that B3 is equal to 0 and B2 is equal to 1, we are going to start to evaluate the CMX operation over the encrypted bits B2. And so we are giving in the LUTs as input. The output will be the correct LUT, meaning that this gives us the LUT of 0 B2 for the first CMX, and this gives us the LUT of 1 B2 for the second CMX. So this is only dependent on the B2 thing. And so if we have a look on the lookup table, this means in fact that we are just choosing 2 rows between all of array of the representing the lookup table. Then, if we apply just 1 more CMX, but this time using the B3 bit as a selector, then we are able to choose the correct LUT. This means in our case that we are choosing the LUT 0, 1 accordingly to the value of the encrypted bits. So now we know in which part of the array we are. So among the 4 LUTs, we choose the correct one. So this is the 0. However, at this time, we doesn't succeed to evaluate the LUT completely because we still have 2 bits on each we need to evaluate the function. So in this case, we are going to use another strategy, which is called the blind rotate. And this is the same blind rotate as in the Bootstrap. And this allows us to choose between 4.1, 4.5, 4.6, or 4.7, the correct one, depending on our inputs. So we're starting with the encrypted LUTs as input, and then we are giving it the 2 encrypted bits to select on it. We compute a blind notation, and this gives us basically the function evaluated on the message. So this is the same blind notation as we use in the Bootstrap. The different thing that instead of giving encryption of the keys for the ones who know how the Bootstrap is working, here we are giving directly the bits of the messages. So this is the main difference between the blind notate of the Bootstrap. And once we have the computation of the function, the correct computation of the function, we still need to make a transformation in order to have the same type of ciphertext in the output. So if we do a little bit of recap, it's more technical, so sorry about that. But if we want to do a recap, we have as input a message M, which is composed of many blocks, depending on the decomposition we want to choose. We start by extracting each bit of all its blocks. So we have like a collection of bits, encrypted bits. And then we want to apply the CMX tree and the blind rotation over the function we choose, represented as a lookup table. And in the end, we are able to get the function evaluated over the large messages. So as we see in this case, so we have many CMX tree to evaluate, CMX tree plus blind rotate to evaluate, because in the previous case we were in the simpler case where the function takes as input many blocks but outputs only 1 block. And so if we want to have an input size which is equal to the output sizes, we needed to do this process as many times as we have blocks. So for each blocks, we need to do this process to output correctly the function. So in a nutshell, the LUT PBS allows us to compute any univariate functions over integers. There is no restriction on function types, and it scales very well with the large size. So we are able to increase the size of integers. This is independent of the integers representation, and it's compliant with the Radix and the CRT approaches. Plus, it does not require a padding bit. And so this is like a very, very cool thing because it allows to improve the precision we can have by blocks, since we have 1 bit more to represent our messages. And it also improves like the carry cleaning thing, because now we can get rid of the carry cleaning. So I will not go into the details now because it's a little bit more complicated, but even using the CRT representation, we are able to getting rid of the carry cleaning so that we don't need to compute the modulus at each times. And so we gained a lot in terms of efficiency. But I will not go into details now, but we are working on this kind of thing. And for sure, it will be added soon into the concrete library. So let's now have a little bit look about the timings if we want to work on 16-bit integers. So if you want to compute additions, in the case of the Radix or the CRT, it's almost free. In the case of the multiplication, as we have seen, the algorithm is quite easier in the Radix case. And in the case of the CRT, we can do everything in parallel way. So this is the cost of Bootstrap. The carry propagations is also like an heavy computation if we compare it to the carry of the CRT thing. Then, so we put the PBS into a different color because we are not using the same parameters in this case. The idea here is to getting rid of the padding bit. So we are evaluating a function over encrypted data, which are not using padding bit, and it takes us 2.7 seconds. So in conclusion, what do you need to remember from this presentation? I guess the main thing is about the new concrete release, which allows you to give to work on large integers without gaining any information about all the details we just have seen. So this is easy to use, and you don't need to understand everything of the previous slides. So this allows you to work on the shortint for sure, as it was previously the case, but everything is much simpler. It allows you to work over large integers, which was not possible before, and you can choose if you go more under the traits over the Radix or the CRT decomposition. So at the moment, in the real concrete, only the Radix are implemented, but we are working on implementing the CRT thing into the concrete. But yes, this needs a little bit of work because we need to choose the best representation possible to have the fastest way to compute. And so we want to give to the user the simplicity we already have now, and we don't want the user to choose between the two representations. So this is work ongoing. So there are still a lot of questions, still a lot of things to do on the concrete, on implementation, and on the new features. A lot of research questions about the representation, for instance, the trade-off we need to figure out between using a padding bit or using a carry buffer, all this kind of thing. So for sure, if you're interested to work on this thing, if you have any feedbacks on the concrete's new API, you're more than welcome. So now just some links to something which might be useful, that are the rest, the crates, the Ciphertext to have access to the code. Everything is open source, so you can have a look on the code. You can have more information in documentation, and if you're interested more in the crypto details, you can have a look on the eCrypt paper. So thank you very much, and if you have any question, I will be happy to try to answer it. Thanks.
Thank you, Jean-Baptiste. Nice presentation, very well done. Do we have any questions? You can directly unmute yourself, say hi, and then ask your question to Jean-Baptiste. Don't be shy if you have a question, just go ahead. I see there are a few questions on the chat. Michael, do you want to ask a question directly? I guess not. Okay.
Hi, can I ask a question?
Yeah, go ahead, please.
Yeah, sorry, just a simple question. So using your WO-PBS, do we still have constraints on the type of nonlinear functions evaluated over the RNS decomposed messages? Like you mentioned that using WO-PBS, you can perform, programmable bootstrapping over decomposed messages, right?
Yeah. So if I understand correctly, the question, you don't have any restriction if you are using the WO-PBS thing on the function.
Okay.
You can,
Can you elaborate? Yeah.
Only true for the CRT-PBS thing, and yeah, in this case, the function class is smaller than just the generic function you want to compute on. So yeah.
Okay, so using WO-PBS, we don't have restrictions on the types of functions over RNS decomposed messages. And can you elaborate on why is that true?
why could be it false?
What?
So no, the fact is we are using the kind of trick to have an intermediate representation, which is more closer to the Radix one. And then so we extract each bit of the thing. And then by using a particular encoding of the LUT function, we are able to getting rid of the CRT constraint.
Okay, get it. Thank you.
May I have a question, please?
Yes.
I would like to, if I understand correctly, the longest, the large integer, the longest type is 16-bit. Is it right?
So we take as example 16 bits because we have some practical results using the PBS over it. But if you want to compute like level operations, for sure you can go further than 16 bits. Even 32 bits, you can do the things. You can have some evaluation function, like using the WO-PBS over 32 bits is also working, but it's much slower for sure. But you have more restriction if you want to compute complicated things without the padding bit, for instance. I can go into details if you want to.
My point is that I would like to compare my approach for multiplication of 32-bit numbers with yours. So what would be the best approach to do this with the new concrete? I didn't look at the code yet. I don't know if this is published. So
the code, everything is released. I guess if you just want to compute multiplication, the best way to go will be to have Radix CRT decomposition, and then to do each of the multiplication separately by using parameters with padding bit.
Okay, so
it's like PBS that you use in a parallel way, so it's like fast.
Yeah, I see. So you mean split the number into smaller numbers and then implement Karatsuba?
So yeah, we can do Karatsuba with the Radix. I think this is for sure.
You're right. This is yeah.
But yeah, for the CRT.
For CRT, you cannot do Karatsuba.
Yeah, we have to think about it, I think.
Yeah, or we at least we need to think about this. That it's not so straightforward.
Jacob, also, I think maybe one of the reasons why we limit examples to 16 bits is because computing a lookup table for the PBS on 32 or 64 bits would be highly impractical. So I think like if you're trying to evaluate a function using the PBS, at some point, the size of the lookup table becomes the actual limitation and not the precision. If that makes sense.
Yeah, I see. For lookup for PBS or for lookup tables, the precision is definitely the limit. But I was just asking about one particular operation if I wanted to do, let's say, addition and multiplication for.
I mean, if you have good algorithms for doing faster multiplication, that would be amazing to contribute. Actually, in general, I would say that any improvement on the library, we would love to have, and we're doing our best, to do as much as we can internally, but. Well, there's a lot to do, right? And
I believe. I would just like to compare my approach for the parallel addition with Radix, with parallel addition algorithm over Radix, with your approach with CRT and Radix, and then see how we are doing.
That'd be super interesting. So definitely.
So I mean, I'm super curious about this, so that's why I'm asking how I can go faster towards this comparison.
Yeah, maybe at the moment, if you only use concrete, this is only the Radix implementation. So if you want to do the CRT thing, you need to go into the concrete integer at the moment. But soon there will be the CRT implementation in the general API of concrete.
Yeah. Okay. Yeah. Definitely. I will have a look at the code. So let also other people ask their questions. Thank you.
You probably want to look at the the underlying libraries directly. Probably not at a high level API in your case. I think you want to.
Yeah. Yeah. Okay. Thank you.
Okay. Anybody else? Okay, so if there are no more questions, thank you very much, everyone. So as always, we can continue the conversation on Discord. Just go to discord.fhe.org. The presentation has been recorded and will be published on the FHE.org website. And if you have something you'd like to present, please get in touch, let us know, and then we can try to schedule that for one of the future sessions. There was a quick question about, will the previous API still be maintained? No, the one with the encodings and everything is no longer maintained. However, we will reintroduce some of those, let's say, fine-grained features in a later release. But right now, the previous API is not maintained. Okay, great. Thank you very much, everyone. Have a great day or evening, and see you in a month.